Hello, everyone, and welcome to our talk. We are very excited to be joined by Dr. Mark Lewis today. Dr. Lewis is the Executive Director of the National Defense Industrial Association's Emerging Technologies Institute, a non-partisan research center focused on technologies that are critical to the future of national defense. Prior to his position, Dr. Lewis was Director of Defense Research and Engineering in the Department of Defense, as well as the Acting Deputy Undersecretary of Defense for Research and Engineering. Thank you very much for joining us today, Dr. Lewis.
Oh, thank you very much for having me. So I thought I'd start out by saying a few words a little bit about my background and my path through aerospace, hit on a few career highlights. Then I'll talk about the area that I'm most passionate about, which is very high-speed flight, the realm of hypersonics. So to start off with, again, thank you so much for the opportunity to talk to this group. I began my career, my interest in aerospace from an extremely young age. So, I was part of the generation that got to watch Neil Armstrong walk on the moon. And from a very, very early age, I knew I wanted to be involved in something to do with space and aeronautics. I did my undergraduate degrees at MIT in the Department of Aeronautics and Astronautics, and also in Earth and Planetary Science. And when I first started out as an undergraduate, I actually thought I might focus on planetary science as a career. But after spending a summer working in a laboratory which was dedicated to planetary science, I realized no, I was much more of an engineer. So finished at MIT, did master's and PhD in aeronautics and astronautics with a focus on advanced propulsion, and then went immediately to an academic career. I began teaching in 1988. I began teaching at the University of Maryland in the Department of Aerospace Engineering, and started as an assistant professor there. In the United States, our ranks, you start out as a brand new faculty member, you're an assistant professor, then you get tenure, you're an associate professor, then you become a full professor. And really, for the beginning of my career, that's what I thought my trajectory was going to be. I was going to spend my whole life at a university. And then, I guess in the late 1990s, I got involved with the United States Air Force. The Air Force has an advisory board filled with faculty members, professors, people from industry, people from laboratories. And really enjoyed that work. It's part-time. You only do it about once a month or so, but it was part-time, but I enjoyed that. And following that, in 2004, is a really neat job. It sounds like a really neat job title, but it actually was a really fun, exciting job. Liked doing that, finished that up after 4 years in 2008, went back to my university job. I'm going to admit I was a little bit bored being back on a university campus after having been in the Pentagon. I went to an organization called the Institute for Defense Analyses, which is a think tank, an organization that really focuses on doing detailed reports on science and technology for the U.S. government, and spent almost 8 years there running an organization that did research for the White House. So in the White House, there's an organization called the Office of Science Technology Policy. It's run by the President's Science Advisor. And we did various reports, everything from energy to environment, but also space, aeronautics. We looked at supersonic flight. We looked at commercial space. We looked at whether there was a business case for commercial space stations. We looked at various aspects of NASA's plans to go to the moon, go to Mars. And then in 2019, I had the opportunity to go back to the Pentagon. And this time, as you mentioned, as the Director of Defense Research and Engineering. So I was in charge of modernization for the Department of Defense. So what does that mean? Well, very simply, it's looking at how we introduce new technologies into the hands of our defense, into to the Navy, the Army, the Air Force, and the Space Force. And so that became my focus. We had a series of technologies. Many of them were aerospace technologies that we were working with all the various players in the Pentagon to try to introduce them, as we say, get them into the hands of the warfighter. And I did that until July of 2020. And then my boss quit. So the Undersecretary of Defense for Research and Engineering was Mike Griffin. Mike had been the NASA administrator. We'd been friends for many years. And he left the department in July. So I stepped up. I became the acting Deputy Undersecretary of Defense. And in that role, I had organizations like DARPA, the Defense Advanced Research Projects Agency. I had the Missile Defense Agency, the Defense Innovation Unit, the Space Development Agency, all coordinated in my office, and all with a research or engineering and technology focus. So I did that until January of 2021, when the administration changed. And then I immediately joined the National Defense Industrial Association, where I am now. And as was mentioned, I'm setting up this Emerging Technologies Institute with a focus on a range of technologies, everything from artificial intelligence to cyber, but space, hypersonics, lasers, direct energy are all part of that portfolio. So with that background in mind, what I thought I would do is go back and talk a little bit about my work in general interest area, the general interest area of hypersonic flight. That is, flight in excess of about 5 times the speed of sound, because that has been the focus of most of my work over the years. At the university, when I was the first time I was in the Pentagon, the second time I was in the Pentagon, even at the Institute for Defense Analyses. So I'm going to try to show some slides, and let's see. Hopefully this is going to work. And I will share screen. All right. So can you guys all, can you see my slides?
Yes.
Yeah.
All right, excellent. All right, so let's talk a little bit about hypersonic flight. And we'll start off by kind of putting it into perspective, right? What is hypersonic flight? Well, I think most of the audience is familiar with subsonic travel. If you've ever been on a jet airplane, you've been in an airliner, you've traveled less than the speed of sound. A modern airliner comes close to the speed of sound, about 8 to 9 tenths of the speed of sound. Of course, we've been flying above the speed of sound since 1947. Chuck Yeager flew the Bell X-1 to slightly in excess of the speed of sound, 1947. We've been flying supersonically since then, and many airplanes around the world are fly at supersonic speeds. Jet fighters, I've got a picture of an F-15 there. They fly regularly at supersonic speeds. There are a number of commercial aircraft, the Concorde being the best example of a supersonic airplane. And now there are a bunch of small startup companies around the world, including in the United States, that are looking at reintroducing supersonic flight. But hypersonic is a little bit faster. So hypersonic is a subset of supersonic, right? So supersonic is anything that's faster than Mach 1. Generally for hypersonic, we say it's faster than about Mach 5, or 5 times the speed of sound. All right. Now, I'll start out by telling you there's no fixed definition of what is meant by hypersonic. All right. I joke, if you get 10 hypersonic researchers in a room, you will get 11 definitions of what hypersonic means. So when you go from subsonic flight to supersonic flight, the basic physics of the airflow changes. The way air behaves over the vehicle changes. Nothing like that happens when you go from supersonic to hypersonic. But there's some characteristics that are important in hypersonics. For one thing, whenever you fly faster than sound, you create a shock wave in front of the vehicle, a sudden jump in pressure and temperature. At hypersonic speeds, those shock waves are pressed very, very close to the surface of the vehicle. Heat becomes really important. When you fly that fast, you get really hot. So you worry about heating on the surface of the vehicle, especially on sharp leading edges. And because of the heating, you worry about chemistry. You can start to break down molecules of the air. That changes the aerodynamics. If you're going fast enough, you actually strip electrons off of atoms in the air. And so you get charge flow, you get plasma flow. All right. Now in modern usage, when we talk about hypersonics, we're really using it as a shorthand. We really mean vehicles that are very sharp and slender and can fly through the atmosphere. Although not all hypersonic vehicles fit in that category. All right, so here's a picture that just kind of shows you the range of various hypersonic systems. Right, on the left-hand side in the upper corner, you see weapons. Right, there are rockets and missiles that can be designed to fly at hypersonic speeds through the atmosphere. Many countries are developing them: the United States, Russia, China. Then there are hypersonic aircraft. You can imagine a commercial airplane that could fly at Mach 4.5, Mach 5. Airplanes that could travel around the world in a matter of hours. And then there are hypersonic vehicles that we might someday use to get into space in place of more traditional rockets. And that would be really exciting because that would mean we could fly up into space with a more airplane-like model as opposed to a rocket model. And you think about that. It is very, very difficult still to launch a rocket. When the United States used to launch the space shuttle, it took an army of people, thousands of people to get that vehicle ready for flight. It took many months of preparation. You compare that to a jetliner. You get on a commercial airliner. It takes basically 15 minutes to get that airplane ready for flight. Right? Airliner pulls up to the gate at London Heathrow or De Gaulle Airport or Dulles Airport in Washington. Pulls up to the gate. Passengers get off. They get the luggage off. They clean the airplane. 15 minutes later, it's ready to take off. If we could operate in space with an airplane-like model, think about how it would revolutionize our access to space, lower the cost. Now, there's a whole other category of hypersonic vehicles, and I show that in the lower part of the slide, and that is anything that has ever come back from space. That means spacecraft, space shuttles, the Apollo spacecraft, the Mercury spacecraft. Anytime you enter a planetary atmosphere, so the probes that enter the atmosphere of Mars, they're hitting the atmosphere at very high speeds, very high Mach numbers, very much faster than the local speed of sound. So they themselves are also hypersonic vehicles. We've obviously been flying those sorts of vehicles for many, many decades. But you'll notice all those vehicles are very blunt. They're thick and they're blunt because we want them to slow down. Right? When a Mars probe is entering the atmosphere of Mars, we're trying to make it slow down. We want it to lose orbital energy. And so we give it a blunt heat shield. The sorts of things we were talking about earlier, the aircraft, spacecraft, weapons, we don't want them to slow down. We want them to continue to fly through the atmosphere. And that means that we're driven towards designs that are very sharp and very slender, low drag. Now, here's my I call it the money slide. These are all the basic research issues that you face when you try to design a hypersonic vehicle. And this is meant as what we call an eye chart. It's a list of lots and lots and lots of different problems that you have when you try to approach the design of a hypersonic vehicle. And I've shown kind of a representative vehicle in the center of that. And then you say all these issues. How do you match the engine to the vehicle? How do you deal with computing the flow inside the engine, outside the vehicle? You've got a chemically reacting flow. You've got very high temperatures. You've got strong shock waves. All these are very, very difficult to model accurately. Hypersonic vehicles, by their very nature, because they're so slender, tend to be what we refer to as fully coupled. So that means the front of the vehicle is actually part of the engine. The back of the vehicle is also part of the engine, right? So the front of the vehicle is the inlet of the engine. The back of the vehicle is the nozzle. So anything you do to the engine affects the overall performance of the vehicle. Anything you do to the vehicle affects the overall performance of the engine. And so it's very, very tightly coupled. And then it's also coupled to the trajectory, right? The way you fly this vehicle, the altitudes at which you fly, will have a tremendous impact on the design and the operation. Now, take you back a little bit in history. We have been flying hypersonic vehicles for many decades. 1948 was the flight of the very first human-made hypersonic vehicle. It was a sounding rocket called the WAC Corporal, and it was flown out at the White Sands Missile Base on top of a captured German V-2 rocket right after World War II. And the fellow that you see pictured standing there is a gentleman named Frank Molina, who became one of our early pioneers in rocketry, but also takes credit for flying this first vehicle. Then from the 1950s, the 1960s, there's a whole series of tests and programs and projects that involve flight at hypersonic speeds. Probably most famous in the 1960s was the X-15 rocket plane. 3 of these vehicles were built. They flew throughout the 1960s. They hold records that stand even today, including the fastest piloted flight in the atmosphere at Mach 6.7. That's almost 7 times the speed of sound in a vehicle, in an airplane flying in the atmosphere. Some other notes. So the fastest that we've ever flown human beings was on the Apollo 10 reentry capsule. They came in at 37 times the speed of sound, Mach 37, very hypersonic. And then there have been some unmanned vehicles. In 2002, a university group from the University of Queensland flew a rocket called High Shot. And High Shot had a supersonic combustion ramjet engine on it. The type of engine we think is the key to flying at hypersonic speeds. They only flew it for a couple of seconds, but it hit about Mach 7.5. And we think that's the record for the first time someone flew a jet-powered hypersonic vehicle. And that was followed in 2004 by a NASA program called X-43. It's a subscale vehicle, but it also flew at hypersonic speeds. And then following that, the U.S. Air Force flew a vehicle called the X-51. And that flew for a sustained period of time for almost 200 seconds at hypersonic speeds. All right, so some more on history. This idea of flying at hypersonic speeds in the atmosphere is that it's not new. It's also not new, the idea of flying using jet engines instead of rocket engines. Right? So a rocket engine has all of its fuel contained. A jet engine uses oxygen, uses air to burn with its fuel. So it's intrinsically much more efficient because you're not carrying that oxygen with you. The idea of doing that at hypersonic speeds dates back to the late 1950s. Two researchers by the name of Weber and McKay did a thought experiment. They said, what would happen if we took a conventional ramjet engine, which only goes to about Mach 3, 3.5. What if we extended the Mach number? What if we kept it operating all the way up the Mach scale? And they thought about this. They worked out the physics of how these engines would operate. And really, it was finally demonstrated first by that Australian experiment, the high shot experiment, and then subsequently by the NASA experiment, X-43, that proved them right about 46 years later. And this chart kind of shows you why we wanted to do that. So this is a plot of something called specific impulse. That is the amount of thrust that you get out of an engine compared to the rate at which fuel is consumed by that engine. So think of this as bang for the buck, right? This is how much thrust you get out compared to how much fuel you're burning. And you'll notice at the bottom of that chart, you'll see rockets. Rockets have a specific impulse that is about a maximum of about 450 seconds. The units of specific impulse work out to be seconds. Jet engines can do much better. If you see a modern turbofan engine, can be in the many thousands of seconds. So you get lots more thrust compared to the amount of fuel that you burn. And the reason for that is very simple. A modern jet engine is consuming air. It's swallowing air into an inlet. So most of the mass that's moving through that engine is coming from outside the engine. As you start moving up the Mach scale, jet engines have a lower and lower specific impulse. If you could build an air-breathing engine that continues to fly at high Mach numbers, powered by that engine I mentioned, the scramjet, you see you have the potential for a specific impulse that's at least twice that of any rocket engine. So you get twice the thrust for the amount of fuel that you're burning. And that's why we're so interested in these air-breathing systems, these jet-powered hypersonic vehicles. All right, now, again, long history working in this field. In 1963, long time ago, the U.S. Air Force had this idea for building an aerospace plane that was going to take off from any runway and fly up into space, all right? Imagine this. This was 58 years ago. And what they discovered was this was too hard to do. They didn't know how to do this. So they canceled the program. It came back, 1986. The United States began a program called the National Aerospace Plane. It was a really big deal. The President of the United States announced it on national television. We're going to build an airplane that could take off from any runway, fly up into space. It was going to have the world in about 2.5 hours. Really exciting program. The problem is, when it was thought of in 1986, this is what the vehicle looked like. And the idea was that airplane would weigh about 50,000 pounds. By 1993, the design of that airplane had grown to 450,000 pounds. Now, a good rule of thumb in aerospace engineering, the heavier you are, the more you cost. Big airplanes cost a lot. And the price tag on this airplane was going to be about $12 billion. And oh, by the way, the deep dark secret was we didn't know how to build it either, right? Almost 30 years after that first aerospace plane, we still didn't know how to build this airplane. We didn't know how to design the engines. We didn't know if the engines would even work. We didn't know what materials to use. We didn't know what fuel to use. We didn't even know if the design would completely close, meaning we didn't know if you could actually, if everything worked as expected, we still didn't know if it would meet its mission objectives. However, in the United States, we kind of backed up a bit and said, all right, let's take a step back. Let's not try to build an airplane that can fly up into space yet. Let's do some smaller scale experiments. And two of those in particular, I've already mentioned, were the NASA X-43 and the Air Force's X-51. And these were both subscale, meaning, small models that were mounted on rockets that were accelerated up to a hypersonic speed. And then they separated off their rockets, scramjet engines kicked in, and they flew for a sustained period of time. In the case of X-43, the NASA missions, they flew twice, both times for about 10 seconds. And you might step back and say, well, 10 seconds, that doesn't sound like a lot. Well, a molecule of air that enters the front of the engine exits the engine in about 1/1000th of a second. That's 1/1000. So 10 seconds is 10,000 flow passages through the engine. That's a really long time on a hypersonic scale. And then the X-51 did it for 210 seconds. So that's almost infinity on the scale of molecules moving through your engine. And that's the X-43 vehicle. I had the pleasure of working on a concept that led to the design of this vehicle. We designed it as something called a hypersonic wave rider, which means it's a vehicle configuration that rides on top of its shockwave. It's a very, very efficient aerodynamic shape. It takes maximum advantage of the properties of aerodynamic flows. It's really efficient in the way it processes air into the front of the engine. And that was X-51. And again, that was the vehicle that proved these scramjet engines were practical. Now, you'll note X-51 looks very different than X-43. X-43 looked very much like an airplane. X-51 is missile-like. But it turns out that X-51 was also a wave rider. There was a shockwave that formed off the nose of the vehicle, and that intersected the lip of the engine. And so that vehicle was riding on top of its shockwave as well. And we did 4 flights of X-51, and I'll tell you, this was kind of the highlight of my career. I got to sit in the control room when this happened. So I had already left the Air Force by this point, but I got to sit in the control room as we flew the first flight of X-51. And we were hoping to get to Mach 5. We got really close, about Mach 4.9. Did it for 143 seconds. So that was about 13 times longer than the previous record held by the NASA mission. And then in 2013, we did the 4th flight of the X-51, and that was fully operational, flew for almost 210 seconds. A good rule of thumb, by the way, is that when you're traveling at Mach 5, you travel about a mile a second. So that means 210 seconds, that means we covered 210 miles while that engine was operating. So truly a remarkable accomplishment. All right, so let me go back. And again, I want to relate this, maybe relate this to my career. When I first started as a brand new faculty member teaching aerospace engineering at the University of Maryland, we had a whole list of questions. We didn't know if those engines would even operate at hypersonic speeds. We didn't know if an engine could do something called unstart. And when you unstart an engine, that means you kick out a strong normal shock wave in front of the engine. And we didn't know if the engine could survive that, if the engine would blow apart if that happened. We didn't know if you could inject fuel in a combustor. We didn't know if the leading edges would get so hot when you're traveling at those speeds that they would even survive. We didn't know about the flow that was traveling along the surface of the vehicle, what we call the boundary layer. We didn't know if it was going to be nice and smooth and laminar. We didn't know if it would be turbulent. We didn't know what the heat would be. We didn't know what flow would look like going into the engine. We didn't know if the vehicle was controllable because of how integrated it was. We didn't even know if you could design a good shape that would survive at those speeds. We didn't know what the engine inlets should look like. Now, if I look at years of work, and this is the work, hundreds of people in the field, we can pretty much answer almost every question on that list. We know the engines operate. We've flown them up to 10 times the speed of sound. Engines can spit out normal shocks. They can unstart, and they'll survive. We've injected fuel. Our leading edges have survived. We've measured the way boundary layers behave, the flow on the surface of the vehicle. We've studied inlets. We know the vehicles are very controllable. We've come up with lots and lots of different designs for these vehicles. And so we've really made tremendous progress in the field. It's been very reassuring. It's frankly been very rewarding to watch over the past few decades. I mentioned one area that I did a lot of work in, and that along with others in the field, and that is that whole concept of a wave rider. And I like to highlight it because it's truly an international concept. So the idea of a wave rider was first developed by a researcher from Scotland by the name of Terry Nonweiler. And Terry eventually moved to New Zealand, but was active in the field into the 1990s. And he came up with this amazingly clever way of designing a hypersonic vehicle. And it involves a process called inverse design, where first you pick the flow field that you want, and then you find the shape of the vehicle that gives you that flow field. And Nonweiler realized that at supersonic speeds, you could do that just by imagining a shock wave and then picturing a portion of the flow behind the shock wave and then shaping the vehicle from that flow. And today, nearly every vehicle that we think of that we designed to operate at hypersonic speeds uses that basic design principle. It gives you a highly efficient design. You get high pressure under the vehicle, so you get lots of lift. You get relatively low drag. And it's beautiful for integrating with engines because you start out by knowing what the flow field looks like. So it lends itself beautifully to an inverse design process where you define the flow going to the engine, and then you find the vehicle that gives you that flow. If you look at the next step of hypersonic vehicles that we envision, and these are some concepts coming out of the Boeing Corporation, Lockheed Martin Corporation, therefore reusable hypersonic vehicles, they all actually follow that wave rider philosophy. Right? They all are designed so that the shock wave that forms at the front of the vehicle is captured on the wing of the vehicle, on the leading edge, and provides very, very good flow conditions going into the engines of that vehicle. And this is kind of a fun place to stop too, because this kind of points to what the future holds for hypersonic flight, all right? At the very beginning, I told you there was a range of applications of hypersonic systems, weapons, airplanes, access to space. Right now, most of the work going on around the world is focused on missiles, weapons, military applications. But from there, we're learning a lot, and it's undoubtedly going to transition to work on airplanes. Some of them could be military missions for surveillance, for intelligence gathering, but that's going to eventually lend itself to commercial applications. Airplanes that can fly not just at Mach 0.8, not just at Mach 1.1 or 1.2, but maybe airplanes that can fly at Mach 4, Mach 5, Mach 6, maybe ultimately Mach 10. You can imagine a flight from New York City to Tokyo in 2 hours. You could fly almost anywhere around the world in 2 hours at those speeds. And think about what that would mean for humanity. Think about what it would mean if you could be at any other country in less time than it takes to watch the onboard movie and have a quick lunch or a bad dinner. So that's kind of where the future holds. And I can tell you right now, hypersonics is probably one of the more, if not the highest priority topic area for a number of organizations in the United States. The United States Army, the United States Air Force, the United States Navy, the Defense Advanced Research Projects Agency, all are investing very, very heavily in hypersonics. NASA, the National Aeronautics and Space Administration, their aeronautics program, does a lot of work in hypersonics as well. So it's really quite a growing area, quite an exciting area, and not just in the United States, but really around the world. In England, in France, in Germany, in Japan, in Russia, in China, lots of activities really focused on this goal of sustained flight at more than 5 times the speed of sound. So with that, let me kind of conclude my formal remarks, and I'd be happy to take any questions that anyone has, either about hypersonics in general or any career questions that I can answer. The floor is yours.
Thank you so much for giving this presentation. It was really interesting. So we have a couple of questions from the audience. So first person asks, are all the trending tech developments based in jet and plasma propulsion? Or will we have something more like in science fiction, like resonance systems to allow levitation and no acceleration limit?
So, look, I always say it's important that we don't try to violate the laws of physics, unless, of course, we can change the laws of physics, all right, or we learn new laws of physics. Right now, I don't know of a lot of different ways to power a hypersonic vehicle. All right, there are basically two ways to do it. One is with a rocket. We know how to do that. And the other is with some form of jet propulsion. Now, I mentioned mostly the scramjet engine, but there are, in fact, other ways that you could power a hypersonic vehicle. For example, there's a company in the UK called Reaction Engines, and they've been working on an amazingly clever propulsion system that essentially uses a cooler that cools the air coming into the front of the engine, takes the heat out of the front of the engine, and then can essentially condenses air, liquefies it so they can then burn it in either a conventional rocket engine, or they can trick a jet engine into thinking that it's flying at a lower speed. Very, very clever idea. So that might be one path to hypersonic speeds. There are other ways you might reach hypersonic speeds. There are some conventional jet engines that you might transition. You might do what's called a combined cycle engine, where you start off with a jet engine and then you transition to a higher speed operation. So lots of different concepts, but I'm not too hopeful on things like levitation for now.
That sounds interesting. It's actually reminding me my courses on space propulsion on that topic. Another question is about your list of things that we don't know yet and
yes.
that we know yet has been very much appreciated by the audience. And for what about today? What do we don't know yet, and what are the main thing we should learn about?
So that's a great question. So first and foremost, I started life as a university professor. So university professors always like to pose questions. They don't necessarily like answers, they like questions. And hypersonics is still full of many, many questions. So I'll give you just one example. I mentioned the concept of the boundary layer. So for those of you who are less familiar with aerodynamics, when we think about the way air flows over a surface, say over a wing or over the body of an airplane, there's a region of air very, very close to the surface that we call the boundary layer. And that's important because that's where most of the skin friction effects occur. Right? In the boundary layer, we see very sharp gradients in the velocity of the air. We see most of the skin friction. We also see most of the heating. So understanding a boundary layer is very important for understanding the overall performance of an airplane. Now, at low speeds, I have a very good understanding of the state of a boundary layer. If, for example, I'm designing a jetliner, if you tell me the speed at which that airplane is flying and you tell me the altitude at which it's flying, tell me how big it is, I can tell you exactly what the condition of the boundary layer will be. And one basic question I might ask is the flow nice and smooth and laminar, moving in streamlines, or is it turbulent? Does it have small eddies and swirls? And depending on whether it's smooth and laminar or whether it's turbulent, that will change the amount of skin friction, so how much resistance I feel. It'll change how hot my surface gets. So it's really important to know this. That's a big unknown still in hypersonics. Right? We don't have a full characterization of when the boundary layer goes from smooth and laminar to fully turbulent. And in fact, in some ways, a hypersonic boundary layer behaves differently than a boundary layer at lower speeds. So that's a big unknown area. Now, here's why that's especially important. So there's a category of questions that we sometimes refer to as unknown unknowns. That is, things we don't know, and we don't know that we don't know. And we contrast those to known unknowns. And an known unknown is a little bit of a tongue twister, but a known unknown means we know we don't know it. But because we know we don't know it, we can design around it. All right, so in the 2000s, the United States flew a vehicle called the HTV-2, the Hypersonic Transition Vehicle 2. And we knew that we didn't really know what the boundary layer would look like on that vehicle. So we designed it accordingly. We said, all right, we're going to over-design this thing. And we looked at two ranges. We looked at the vehicle as if the boundary layer were completely smooth and laminar. and we looked at it as if it was completely turbulent. And we said, okay, we've got those two bounding points. Reality is going to be somewhere in between. It's going to go from smooth and laminar to turbulent at some point in the vehicle. And so we'll bracket the results. It turned out that our assumptions were completely wrong about that vehicle. Our lack of knowledge of the boundary layer was so severe that, in fact, we wound up losing the vehicle. It didn't survive its flight test because of our lack of understanding. So that led to a lot of experimentation, a lot of ongoing modeling. So that's a big unknown. Other things that we don't know about. So I mentioned at hypersonic speeds, the temperatures can become so high that chemistry starts to become important. All right, at high enough speeds, the molecules of oxygen in the air start to rip apart. So you go from O2 to individual molecules of O. At sufficiently high speeds, high Mach numbers, nitrogen molecules start to rip apart. That changes the behavior of aerodynamics. And so that's another one that we're still working with, that we're still exploring. Whole range of topics. We last year in the United States, we set up a consortium of universities to tackle all these fundamental problems. We've got about 50 universities now working in this consortium, and total investment of about $100 million, covering this full range of topics. That's enough money to keep a lot of professors, a lot of graduate students, a lot of postdoctoral researchers in business for a very long period of time.
Thank you. Someone said testing hypersonic systems is very expensive. Do you have any thoughts on cost-effective methods for fielding next generation hypersonics?
So, the questioner is absolutely right. Testing at hypersonic conditions is expensive. To do it right, you need to, as accurately as possible, simulate real flight conditions. That's really difficult to do. To recreate the energies associated with flying at 5, 7, 10 times the speed of sound requires very, very extensive facilities. There are wind tunnels around the world that can do that. And what you'll find is that no one wind tunnel can do it all, right? It's a basic principle that, a wind tunnel might be able to simulate one aspect of hypersonic flight, but not simulate the other aspects. I'll give you an example. In the United States, we have a wind tunnel that is operated by the United States Air Force that is given the rather unglorious name Hypervelocity Wind Tunnel Number 9. We just call it Tunnel 9. By the way, why is it called Tunnel 9? Well, Tunnel Number 1 was a wind tunnel that was built by Wernher von Braun during World War II. And after the war, it was captured by the United States military, and they brought it to the United States and assembled it. It was the wind tunnel that von Braun used when he designed his V-2 rocket. And then following that Tunnel Number 1, the United States Navy built a whole series of wind tunnels. So Tunnel Number 9 was the 9th in that series, right? So the way Tunnel 9 works is it's designed it looks a little bit like a rocket engine in that you've got a big nozzle. You have a supply of air at extremely high pressure. And when you want to do a test, you break a metal diaphragm. That high pressure air goes racing down that nozzle. It expands down the nozzle. As it goes down the nozzle, it goes faster and faster. But the temperature gets lower and lower. And so you wind up with sending air into a test section that can go at very high Mach numbers. Tunnel 9 can test up to 18 times the speed of sound. Absolutely remarkable. But the air in the test section is at very low temperature. So it's not accurately reproducing the temperatures that you experience. Even worse, because of the way the tunnel operates, they can't have oxygen inside the tunnel. So the air that's moving through that tunnel is pure nitrogen. So it's not quite the right chemical mix. So you can measure some properties. You can measure forces. You can measure lift. You can measure drag. But you can never put an engine in Tunnel Number 9. We have other tunnels that will measure engine performance. So NASA, National Aeronautical Space Administration, has a wind tunnel at their Langley Center, which we use to test engines. And it will test a scramjet engine for many seconds. It's probably our best test facility for measuring the performance of a scramjet engine. Well, in order to get the temperatures necessary for an engine to operate, that Langley tunnel basically burns fuel upstream of the engine. to heat up the air. So the gas that goes into the engine isn't exactly the same air composition that a real engine would see. So every wind tunnel is off a little bit. So what we actually argue is you need a combination. You need multiple wind tunnels. You need wind tunnels that look at various aspects of hypersonic flight, outside aerodynamics, engine performance. But then equally important, we need to do flight tests. And that's why, when the Australians wanted to fly their very first scramjet, they put it on a sounding rocket. When we wanted to see if scramjet engines would really work here in the United States, we put it on a rocket that was the NASA X-43, and we flew it off the wing of an airplane. So it's really that combination. Now, there are some people who think that we don't have to do testing anymore, that we have arrived at a point where all you do is run computer codes. My own opinion is we're not even close to doing that yet. In the days of that National Aerospace plane program that I mentioned, so that was 1986, so 35 years ago. At the time, there were people who thought that we didn't need wind tunnels. We could do it all with computer codes back then. And the computer codes were very primitive compared to what we have today. Well, they were wrong then. And even today, we know they're wrong. Computer codes are an important part of what we do. We match the results of computers to ground test and flight test, but only used in combination.
Great. That sounds very interesting. Another question is about the scramjets, and because the performance efficiency is based on the velocity of the airflow.
Mm-hmm.
And what's your experience using other hybrid propulsion system to reach efficient scramjets operating ranges?
So great question. The question is about the efficiency of a scramjet engine and overall efficiency of engine. So if you recall from my plot, the higher your speed, generally the lower your specific impulse. And to be perfectly accurate, specific impulse isn't what we technically refer to as inefficiency, although sometimes people use it as efficiency, right? Inefficiency is really a measure of how much energy you get out compared to how much energy is available. A jet engine today, a turbofan engine, like something that powers a jetliner, is perhaps the single most efficient machine ever invented. It is a marvel of modern technology. So I'll give you an example. A typical jet engine operates somewhere close to about 70% efficient. That means about 70% of the energy that's available in the fuel actually comes out as useful work from the engine. Rocket engines do a little bit better than that. Rocket engines can be in the 90% efficient. So 90% of the energy that's in the fuel comes out as kinetic energy out the back of the engine. Now, let me give you some comparisons. A typical automobile engine is doing well if it's about 20% efficient. The human body, and we think of nature as being this marvelous engineer, the human body operates somewhere around 10 to 15% efficiency. So typically, a human being consumes has to consume about 2,000 calories a day, kilocalories a day. Your body actually only uses about 200 of those calories. The rest is lost as waste heat. I mean, your bodies are constantly giving off heat. We're very inefficient machines, as it turns out. All right. So if you look back at those propulsion systems, knowing that propulsion systems can be efficient, why does the specific impulse fall off with Mach number? Well, there are two pieces of that. There are two parts of that efficiency. The first is the way the engine operates itself. It's what we call the cycle efficiency. The other part is what's called the propulsive efficiency. That's the way that the engine uses its energy to provide useful thrust. That's air coming out the back. As you climb up the speed scale, the cycle efficiency will tend to decrease. But more importantly, the propulsive efficiency tends to decrease. And I'll explain that really quickly. So a rule of thumb is the more air that you move over a smaller change in velocity, the more efficient you will be. That's why when we build helicopters, you give them really big rotors. They're moving lots of air, relatively small velocity. If you look at jet airliners over the years, the engines have gotten bigger and bigger and bigger. The inlets have gotten larger. That's because the more air that you swallow into the engine, the more efficient the engine will be. Well, we're constrained with a higher speed aircraft. Right? As you go higher and higher, you have to make the inlets smaller and smaller. It's especially true at hypersonic speeds, where the inlets have to become small to fit between where the shock wave forms and the rest of the vehicle. So that limits your efficiency. But something else interesting starts to happen, which is that as you go to those high speeds, the change in velocity through the engine gets smaller and smaller. If I'm traveling at 5 times the speed of sound, then the speed of the air coming out of the engine is only slightly higher than the speed of the air that came in the front of the engine. And that starts to recover some of your efficiency. So we think that scramjet engines can actually be efficient. Now, a really good question is, what is the maximum speed of a scramjet? All right, to date, we've flown them at Mach 5 for long periods of time. We've flown them at Mach 7. We've flown them at Mach 10 for short periods of time. What is the maximum speed? And the answer to that question is, we don't know. We're not sure. Back in the days of the National Aerospace plane, people thought, yeah, we can do 25 times the speed of sound. Probably can't do that. But can we do Mach 12? Possibly. Can we do Mach 14? Maybe. That remains to be seen. Something to remember, if you think about, energy is proportional to the square of your velocity. Power, that's the rate at which energy is utilized, is proportional to the cube of velocity. So that means that when you double your velocity, you increase your power by a factor of 8, right? So flying at Mach 10 isn't just twice as hard as flying at Mach 5, right? It's about 8 times harder. And so that's why we don't know yet where the limit of speed will be for scramjets. But I expect we'll be pushing that envelope to ever higher Mach numbers.
Thank you. That's fascinating. Going back to the subject of testing, does artificial intelligence currently play a part in the testing and development of hypersonics? And if so, how?
Oh, so that's a very timely question, because everyone's talking about artificial intelligence. Everyone is talking about how artificial intelligence is going to change the way we do things. So far, there hasn't been a lot of intersection between artificial intelligence and testing. But I will tell you that there are techniques that you can apply that are similar to artificial intelligence in vehicle design. So, I mentioned those wave rider shapes as being one of my favorite concepts and an interesting way to design a hypersonic vehicle. So in describing it, I said that when you design a wave rider, you start with the airflow. You figure out what the flow field would look like, and then you figure out the vehicle shape that gives you that flow field. That process lends itself very well to the process of optimization. And in optimization, you define your parameters, and then you allow a computer program basically to come up with the best answer, in this case, the best shape for a given performance parameter. So for example, I might want to design a hypersonic shape that gives me the maximum ratio of lift over drag. A human being would look at it and say, I've got so many options. I've got so many choices. How do I do that? But a computer program running an optimization scheme can actually very effectively go through all the choices and do all the trades and get to a point in the design space. I've had many graduate students who've worked on that process over the years, looking at different ways to optimize these vehicles, optimizing them for volume, being able to stuff a lot of stuff in there, optimizing them for minimum drag, optimizing for certain flow properties going to the engine. And every time you go through a process, you often find that the computer is frankly so much better at getting an answer than the human being. Oftentimes you get an answer, you have to step back and say, well, why did the program come up with that answer? And you have to kind of trace back and figure out what steps it went through to get to a given solution. Now, one of the things that you sometimes find in that process is computers can be very, very literal. So for example, if you build an optimizer, you do an optimization program, you say, find me the shape that gives me the absolute maximum ratio of, might indeed give you maximum lift over drag, but it could have really bad volume. Maybe really thin. There's no room to put any cargo. There's no room to put passengers on board, right? And but the program will do what you told it to do. And so playing with those parameters, saying, hey, I want a combination. I want good aerodynamic performance. I want good lift. I want low drag. But I also want to have a certain amount of volume so I can fit, cargo, passengers. When you start making those trades, then computers can be very, very helpful in exploring the whole design space. The end of my talk, I showed those pictures of airplanes, of some hypersonic craft. Some of those were from the Boeing Corporation. They were developed by a researcher named Kevin Boca. And Kevin is probably the world's leader in this whole area of vehicle design. And he uses these optimization techniques to come up with all these configurations and all these shapes that, frankly, a human being could never do.
That's very interesting, and it's raised question about the future and how to use computer. Another question is about, yes, you said that everything hypersonic planes are developed to reach outer space or intercontinental transportations. But the thing is, if we go out of the atmosphere or very high altitude, there will be a lack of oxygen. And
Absolutely.
So what do we take as oxidizer for tanks for the combustion?
Absolutely. You're exact. That's also an excellent question. So obviously, if you build a hypersonic space plane that's flying up to space, at some point, the air-breathing engines can't work. They're out of air. And in the days of the National Aerospace plane, it was going to have rockets on board. So you'd fly as fast as you could on jet engines. And then at the end of the flight, you'd switch over to rocket power. By the way, we also use rockets for getting up to hypersonic speed. So among the programs that I mentioned, the Australian High Shot program, NASA's X-43, the Air Force's X-51, they all used engines that could fly at hypersonic speeds, but they wouldn't work at low speed. So you had to get it to its hypersonic speed. So how do you do that? Again, you use a rocket. That's why those were all mounted on rocket motors.
That's yeah. Mathilde, if you want to continue, I take it.
Okay. Yeah. So we have another question from the audience. What would you say is currently the biggest limiting factor to achieve long period hypersonic travel?
Simple answer: money. We know how to do the technology. I mean, we have an idea of what the vehicle should look like. We know how the engines should work. So the obstacle is really the investment. And if you think about the commercial applications, right? So the first time you build anything, it's going to be very expensive. So the trick is, can you build a hypersonic airplane for long-term travel at a reasonable price, and can you make it economical to operate? Can you make the ticket price low enough to operate? We have examples where we have failed with those sorts of systems. The Concorde was a magnificent airplane. It never made any money. Many reasons for that, but eventually, as I think you all know, we stopped flying the Concorde because it was losing money. So you'd have to design a hypersonic aircraft that was affordable, not just to develop, not just to invent, build it, and operate it, but so that you can continue, that you could sell tickets at a reasonable price.
That's a good point. And on that point, I saw a discussion on the other day, speaking the comparison between hypersonic commercial flight vehicle against suborbital flight vehicle like SpaceX is developing, like for mass transportation. And what do you see in the future? Like, are we going to have more supersonic flights, Concorde-like, or more like rocket flight, suborbital flight to go from one continent to another?
Yeah, so there's a lot of, every couple of years there's interest in doing that sort of rocket-powered flight. The idea is get out of the atmosphere as quickly as possible, use a rocket, go up to space, and come back down. I'm very skeptical about rocket transportation for the average person. All right, so think about most of these concepts involve using very big rockets. I'm picturing my 92-year-old father trying to strap himself into a rocket and survive 3 Gs at liftoff, flying all the way up into space and then landing again. I think a large segment of the population just won't be able to do that. Plus, remember also, rockets typically require a special launch location. A lot of launch structure. You need, launch pad, launch infrastructure. Whereas an airplane can take off from almost, any long runway. So I'm not very optimistic about the future of rocket point-to-point flight. Maybe someday, maybe. It's always dangerous to say never. But for now, I think we're much likely to see more airplane-like operations than rocket operations.
Do you think there is a future for horizontal launches of rockets then, like Virgin Orbit is doing?
So, horizontal rocket, that's an intriguing question. So there are a lot of reasons that you want to launch horizontally. If you think about it, going into space really isn't about getting altitude. Earth, you could orbit the Earth 10 feet off the ground, right? It's a matter of having enough speed so that you're in free fall conditions. And so, when we launch a rocket, for example, when we account for all the energy that goes into a rocket launch, one of the things that we have to account for is something called gravity loss. When you go straight up, you're just expending energy to fight gravity. And saying that there are a lot of reasons that you want to launch horizontally. Now, the catch is, it's really difficult to launch horizontally off the surface of the planet. Hey, we should launch from an airplane. Use an airplane as your launch platform. It's, the Virgin model. Orbital Sciences did it with their Pegasus rocket. They're now part of Northrop Grumman, but they built the Pegasus rocket to launch satellites up into space, launch small payloads. And they bought a commercial airliner, an L-1011 airplane, and they mount their rockets underneath the airplane. All right. That sounds great. Except if you start working through the design, you realize that there are some fundamental limits to airplane launching of rockets, right? For one thing, you actually don't gain a lot of energy. Right? The amount of extra energy you gain from launching off of an airplane is relatively modest compared to just launching from the ground. So that's problem number one. Problem number two, you're very much constrained by the weight of the rocket. So an airplane can only carry so much. So it limits you to the size of a certain rocket. Paul Allen, the U.S. billionaire, created this company called Stratolaunch to launch large rockets off of a big airplane. I actually help advise Stratolaunch right now. And their original idea was they'd build the world's largest airplane as a launch platform for rockets. That was one possibility. You need a really big airplane to launch a really big rocket. But when all is said and done, you ultimately realize that when you do that, when you launch a rocket off of an airplane, the airplane has really just become the first stage of your rocket. And it's not a very efficient first stage. So every analysis that I've seen suggests that you really don't get a lot of benefit from launching off of an airplane. You're better off just building a more efficient first stage on your whole rocket system.
Okay, great. Maybe we are running out of time, so I don't know if we have time for last one, Mathilde. Or...
Yeah. Thank you so much for coming. As a last question, maybe, do you have any advice for students as in the audience or who want to go into that sector in the future?
Sure. Well, several pieces of advice. First, look, aerospace is an incredibly exciting field. I think my belief is that most of the people who pursue what we do pursue it out of this absolute passion for flight. And I would be willing to bet that if you're in this audience today, you feel that same passion for flight, for moving through the atmosphere at very high speeds. So first, obviously, if you want a career in the field, pursue it, be passionate about it, get the right education. We're a very highly technical discipline, right? Background in aerospace engineering, an understanding of propulsion, aerodynamics, controls are all critical to this. And then you'll find, I think there are many, many opportunities. That hypersonics is a really big area right now. Lots of investment in the United States and around the world. Aerospace companies around the world are looking at various concepts for hypersonic systems. There is a large demand right now for a workforce. At least in the United States, all the companies are looking for people who can work in this field. So if you do well in school, if you pursue this passion, you've got lots of opportunities available.
That's great. Yeah, I think passion is the main driver for everyone, and it helps to reach your goals, even for.
Absolutely, yeah, absolutely. I agree. I'll close. Was complaining about people expecting her to be passionate about aerospace, and she was complaining about this, and I wanted to rip up that editorial and throw it in the trash, because no, we're all passionate about it. That's why we do what we do. That's why we're not doctors or lawyers. That's why we're not the bankers. We're not because we want to build things that fly. We want to build things that expand the horizon, and that carries us all a very long way.
Thank you so much for the advice and the talk. And I'm really sorry if we didn't get to answer all questions, but that's all the time I had for today. So thank you again so much for coming.
Well, thank you so much for having me. I really enjoyed talking to this group.
Thank you very much.
All right.